So the big picture last time where we left off is that we were talking a lot about how to construct electrodes that you could use to either record from the nervous system or stimulate the nervous system. And we're going to continue on that for just a couple of slides here. Then we'll switch gears to so-called spike sorting, and then we'll be finished with handout number 9. Okay? We're going to switch gears here a little bit. We're still talking about recording from neurons, but what you're seeing here is a top-down view of, imagine a piece of silicon where you've gone ahead and etched into the surface of that very flat mirror-like silicon little wells, little indentations, okay? And there's some cross members in here, some little scaffolding and so forth. And then you've put down some, think of them as baby neurons, okay? Very sort of young neurons. And you watch them grow. So in this case, these are 8-day-old neurons, okay, on a so-called neurochip. And what you can see here is a little hard to see exactly what the cell body is and everything, but you can see these processes coming out here. This isn't dirt. These are the fledgling little axons and neurons that go ahead and grow. And so what in the world is going on here? Well, this is very much not going ahead and in a person or in an animal, inserting tiny electrodes to observe natural ongoing neural activity, certainly not during behavior. But what it is it's going to give good recording quality from these 16 different contacts of a neural network, if you will, of a system of neurons that are probably spontaneously firing action potentials, and they're wiring up together. So it's for a different purpose, a different goal, but again, it's a neural electrical interface that's representative of a whole branch of type of research. So the types of things that this is done for example, is studying a whole variety of different types of neurons, how they respond to different pharmacological manipulations. So you could spritz drugs on this if you're using it to screen for what types of medicines might be good for human consumption at some point. Cardiac myocytes, so the little cells from your heart, right, that are electrically responsive. You could watch them beating under a microscope. You could actually see them contract while you're recording their electrical activity. So this is a very interesting platform for doing that type of recording. Okay, so I won't belabor it more, but there you can see the big picture. Okay, so now let's return to this picture of wanting to go ahead and establishing neural interfaces with the brain. Okay, by that I mean an intact brain where the person or animal are actually doing things. You're wanting to read out what their thought processes are and so forth. Okay, and that's what we'll get to within another 15-20 minutes here in lecture today, where we'll flip the switch and we'll go into full decoding mode. It'll be a real sort of sea change in the class as we move in that way of thinking. Okay, so chronic implantation. Chronic just simply means long term. Think about many days to many years. Biocompatibility basically means that what you put in the nervous system may or may not make the brain happy. Okay, it could it will certainly detect there being a foreign object. And what does the body like to do, by the way, with foreign objects in it? Attack them, yeah. So the body senses there's something in there, right? And we'll try to so-called wall it off, build up cells around it, or trigger the immune system to try to go and fight it. It doesn't know if it's going to be harmful. So if you just took a piece of raw silicon, right? You usually think of silicon as pretty inert, and you put a little pebble, if you will, or a little chunk of silicon. You put that right inside of your arm, or you put it right inside of your neck or your body or your brain. What do you think happens? I mean, it's just sand. It's not that big a deal.
Encapsulation, so you're probably going to get a lot of astrocytes surrounding it just where your signal.
Yep. So astrocytes or glial cells will go ahead and wrap it around it and wall it off. So, I mean, this is not, hopefully none of you have shotgun pellets in you, but but we probably know from popular media or news reports that often little pieces of a bullet, a buckshot or other types of things are actually left in the body, right? Instead of going and trying to fish them all out, if they're tiny enough and maybe just in muscle, they'll get walled off and they'll just sort of sit there forever, right? As long as they're not eluding anything toxic, lead might not be the best thing, but silicon would be just fine. So on the one hand, it's fairly safe. It just gets walled off. It's not a problem. But on the other hand, that walling off process, you take some foreign object and you build this, maybe 1/10 of a millimeter thick sphere around it, will cause whatever that is you put into the body not to work. So if that thing that you put in the body was an electrode, and you had to measure electrical current, and it had this wall built up around it, okay, that could be a problem. So that is really biocompatibility, whether the body recognizes it as similar enough, it doesn't get too angry at it, or if it completely walls it off. And then the stability of the interface is also what we were foreshadowing a second ago, which is that if it does get walled off, it could stop working as a good sensor. Okay? So chronic implantation studies are important, of course, for a whole variety of basic science and clinical application reasons where you want to stimulate or record. And the future use of microelectrode arrays, right, these little electrodes that we've been looking at in humans, biocompatibility and stability will become crucial. I'd say that it is crucial now. But certainly if you were talking about putting a system in the brain and wanting to work for a decade, it better really work for a decade, okay? And we're just not quite there yet as a field. So let's just get some rough numbers in our minds. So stimulation electrodes, like cochlear implants or deep brain stimulator systems that we talked about early on in the class, can remain functional for years to decades, while recording electrodes, used for what we'll be talking about in the next two handouts, motor communication processes or prostheses, currently remain functional only for maybe months to years in animal models or in people. So why is there this asymmetry? Why could you put an electrode in and use it to stimulate, and that could work for, say, a decade? But to put an electrode in and have it record, maybe it only works for a few years. Any thoughts on why there's that difference?
More selective?
For recording, you do need to be more selective to a certain extent, but you also want to be selective when you stimulate.
So stimulation is occasionally, and recording is all the time.
That's another good point, yeah. So you could do something, so I think that actually points to the answer, which is when you stimulate, you're passing current from the electrode out into the body. And you're only doing that occasionally. So what you can do is you can get away, by occasionally I mean maybe 1 pulse every second, for example, okay? And so even if there is that walled off area, which there is, you can turn up the current, and because you're doing it not too often, you won't deliver too much power. You can actually stimulate through that. You can pass a current through that wall and go ahead and activate your circuit. But if you have the same electrode and it's walled off and you're trying to just listen faintly all the time to these nearby neurons, that wall will just, for example, take the microphone farther and farther away from the person you want to hear. It will take the sensitive tip that's getting access to that extracellular voltage farther and farther and farther away from a poor neuron that's being sort of pushed back. So that's the asymmetry. Okay? So there's a lot of research underway to really characterize and extend this useful lifetime. Okay? We've already talked some about flexible substrates to minimize the effect of micromotion. That means, right, remember the pin and the jello analogy we've used? Okay? Nerve growth factors infused into the electrode coatings. That's to get the body to like it better. That was that cone electrode we were talking about at the end of class last time. And anti-inflammatories to minimize the implant-induced immunological responses. So when you put in an electrode for the first time, there's no way to avoid the fact that you are rupturing some vessels, you are maybe impaling a couple of cells or maybe a handful of cells. So that will cause an inflammatory process, right? Part of your body's immune system right? You know, if you exercise too much, you get inflamed. Everybody's taken ibuprofen probably at some point in their life to reduce that inflammation. So you could go ahead and coat the electrodes with some sort of anti-inflammatory. So when you put it in, it automatically delivers that mitigating drug right there at the site of action. Okay? It's called a drug-eluting device, where you can have coatings that actually slowly release that. Okay. So that's all we're going to say about electrodes, about how we need to be cognizant of how they sit in the nervous system, in the brain, the types of problems you could run into, the types of things you would want to think about if you want to improve them. And now, for the next few slides, we're really ramping into then our start of handout 10. So let's just sort of take a big picture for a moment here, okay? So here, I can blank this. Okay, so let's consider that for the last 4 weeks or so, we've really been studying how individual neurons work, their electrical properties, their ability to signal from one neuron to the next. We've learned a lot about action potentials, their spiking statistics, their probabilities. Do we model them as Poisson processes or gamma processes, right? And we've also talked about the actual building of the sensors. Okay, now let's abstract ourselves up one level, right? So we'll leave all that behind, okay? Hopefully, you know, don't forget about it, right? Okay, but that's our background to some extent for what we'll do next in the class, right? We're just building on our own material. So what do we want to do next? What we want to do next in sort of this neuroelectrical engineering, right, the title of the course, is we want to understand more about that information and what we can do with that information, okay? How do we eavesdrop in on those electrical pulses, make sense out of them? Remember, we were talking about tuning curves? So we've been foreshadowing all this, but we need to put it all together, okay? We need to understand how electrically we're going to record from those neurons, the types of signal processing we need to do to those electrical channels, and then how we're going to combine that information across many different electrodes, because each electrode can only record from, let's just say, one neuron, and we know that no one neuron tells you the whole story. One neuron is like one piece of a jigsaw puzzle, and we seek to understand the whole picture, so we need many, many pieces. We need many neurons, okay? So the starting point now is to imagine ourselves on this side of an electrode that's touching neurons, okay, or right outside of neurons. And that's what we're going to do for the whole rest of the class. We're going to try to understand how we can take that information out, work on it in real time, how we can build the types of systems we've already seen, think about other future systems. That's where, in a few weeks, our guest lecturers will talk about other types of systems for vision prostheses, okay, for writing information into the cerebral cortex to give you artificial sense of touch, for example. And what we'll be focusing on, because we have to choose one system to try to go into any meaningful depth, is really reading out signals to guide prosthetic arms or computer cursors on a screen. Okay? Does that make sense? For me, at least, it's always easier to care if you sort of always have that big roadmap in mind. Okay. So we have an electrode in the brain. And on the tip of the electrode, we will not record from just one neuron, as I just said we would. We often have a couple of neurons and the electrode sits in between, and maybe we hear one louder than the other, and we must, for at least the purposes of this class, tell the difference between those two neurons. Why is that? Because one neuron may be encoding information in one way, the other neuron may be encoding information in another way, and if you just put the two together, the two signals could wash out. One could respond more for a rightward arm movement, one could respond more for a leftward arm movement. I'm sorry, respond less for a rightward arm movement. So you put them together, you don't get any differentiation. Now, what does this look like? Okay, so this now is the style of plot, unlike those classic pictures in the book of action potentials, right? We've seen action potentials many, many, many times. But this is, I don't know, this is recorded recently, plotted in MATLAB, right? So it sort of has that look of, oh yeah. And also it should have the look of the types of things that you'll do in your upcoming homework sets, okay? Where you take real data, real data previously recorded, data structures that we'll put online. You'll be looking at the data and so forth. So what we have is we have microvolts. Okay, here's 0, here's 800. So it's all less than 1 millivolt. Okay, and that's the voltage coming off the tip of the electrode. Of course, we amplify it, okay, to record it, but this is dividing back down through that amplification to get the so-called, sensor referred voltage. And this is time, so this is 1 second. Okay, now what you're seeing here are a couple of features that I don't think we've really thought a lot about or talked about in class, certainly. Now, one feature that we have is that on this time scale of 1 second, an action potential, which is on the order of 1 millisecond, will be very small. It'll only be 1,000th of the width of this whole 1 second plot, right? So that's what these very sharp lines are. Now, if you zoomed in, right, you'd see the actual action potential shape. Because this is a recording done at about 30,000 samples per second on an A to D converter, okay? So it has that full resolution. But plotted on this time base, you see these very sharp deflections and these very tall ones, which I put a red oval around. Let's say that that comes from neuron number 1, okay? And it's higher because your electrode tip happens to be very close to it, so you're hearing it louder. Now remember, action potentials are all about the same, several tens of millivolts across the membrane, okay? But when you come outside, remember we're not recording from the inside to the outside of the membrane. This is just an electrode in the extracellular space. It's just sitting outside the cell, okay? So what you're recording is just these stray ionic currents from outside the cell. So it'll tell you when there's an action potential, but you can't expect the voltages to be the same. Again, this is less than 1 millivolt, and we know that a peak-to-peak action potential is on the order of 100 millivolts. So we're seeing about 1% of that signal size. Okay? Now, if the electrode is close to neuron 1, there could be another neuron, but neuron 2 that's at a farther distance. And if the signal strength is the same, 1 millivolt, but the currents on the outside have to go farther, you'd expect to find a weaker signal. And that's what's circled in green. So this green is meant to exclude these ones that go way on up high here. So these action potentials that stop all about this height here, you could hypothesize come from a second neuron. Does that make sense? Okay. Now in the coming couple slides, we'll zoom in on this. We'll look at the data in different ways and convince ourselves that that's the case. But it's pretty much that it's pretty simple, okay? Now it's pretty simple in this case that I happened to pick to make it look so simple, okay? Now what if two neurons were sitting here and the electrode were right in between? Well, then just that height difference would collapse. You'd find maybe these peaks go down to here and these peaks go up to here, and you couldn't just look at it and say, oh, there's such a nice voltage difference, okay? But what there always, well, no, not always. What there often is, but not always, what there often is because the two neurons are sitting even the same distance from the electrode, but there's different intermediate fibers and other things in the media, you'll get slight shape distortions, okay? Now, we've always thought of and learned about action potentials being identical, right? And that is absolutely true to first order, okay? But when you're listening to those action potentials, not from across the cell membrane of a given cell, but from outside, you have to keep in mind that those currents are going through whatever medium is out there. And it's not just fluid, but there's also other action potentials, or sorry, other axons or other cell bodies. Okay, maybe there's a silent neuron there, like dark matter, right? Silent neurons that don't fire, you don't hear them, but they still sort of block the current. So what you can see is you can see the action potential, the classic shape, get slightly mutated. And we can use those slight shape differences to tell the two neurons apart. This whole process is called spike sorting, okay? Or action potential sorting, telling two apart. All right, let me pause for a minute here. We've covered a lot. I think it's simple, but we have covered a lot of ground. Let me see if there's any questions, at least in terms of the big picture of where we're going before we delve into this a little bit more in detail. Yeah.
So if they happen at the same time, is that, I think I asked this last class afterward, but it still doesn't seem clear to me what happens and how you would tell.
Yeah. Okay, so this is another degenerate case. Let's say that you had, well, it could be two neurons that are of the same distance from the electrode or different distances. The key point is, what if they fire at exactly the same time? Okay. What will happen is that you'll get so-called spike overlap. Your electrode will hear this neuron and this neuron both emit their action potentials at the same time. That will cause extracellular currents that the electrode will pick up on at the same time. And what you would get to first order is the summation. So if you imagine this action potential and that action potential added, you may get something way up here. Okay? Now there are detailed algorithms. This is where some very interesting machine learning and graphical modeling and so forth comes in, which is to say, well, wait, I just got this super high event. I wonder if that's actually due to two of them firing at the same time. I wonder if I can decompose it and get that shape. And if so, then what I say is neuron 1 and neuron 2 both fired at the same time. Remember the goal of this. The goal of this is to basically get a vector of times that neuron 1 emitted an action potential or fired an action potential, fired a spike, and another vector of times when this one did. And so in that case, you may get the two vectors that have two identical entries of time. That can be hard to tell. And the other big picture point is it's very rare. Okay, only if you have two, let's call the two neurons independent, right? Okay, so let's make a good question. So what are the chances of those two neurons firing an action potential at exactly the same time? Well, it's clearly low if they both have low firing rates, 10 spikes per second, 20 spikes per second. But if they're both firing away gangbusters, 500 spikes per second each, then the chances are going to go up. So it turns out because firing rates tend to be sub 100 spikes per second in cortical neurons, that it will happen, but maybe it'll happen with a 1 or 2% rate. You know, only 1 or 2% of the time